Now, this one is some very interesting work that's being done by the European Broadcasting Union to capture and measure streams in real time. They've actually produced some open source software and some other tools. So, this is a very interesting technology. And we have Wim Vermost and Yevgen Kostiuk, who are both full-time staffers at the EBU in Geneva, and they can tell you about the great little piece of software that they've created. So thank you.
Thank you, Wes. So, welcome everyone. Let's check. You hear me? More or less. So they will pump up the volume at any time. So my name is Willem Vermost. Here on the side you see my colleague. That's Ievgen Kostiuk. Did I do right?
It took him some time.
Yeah, it took me 2 years to be honest, but please be seated and come here. So, high precision capturing and measuring of 2110 streams using commodity IT equipment. It's a mouthful, but I always thank my colleague for hurting me with such long titles. But anyway, let's go through it and let's see if this thing clicks. Is there a technician in the room?
Is there an engineer in the room?
Hold on. I had to unplug that.
So meanwhile, while it's probably the USB key that was unplugged, so I'll go to the other side of the screen to make some room for Yevgen. Hey, look at this. So actually on this open source tool we worked with 3 people. So the middle guy is not here at NAB. He would have loved to be here, but unfortunately he stayed in Portugal, which is an interesting country to be. So let's move to the next slide. So Wes mentioned something about an open source tool. The open source tool is called EBU Live IP Software Toolkit. And actually we use this thing as an offline tool to capture data, process it through the tool, and then look at all the beautiful values. The values that Mike told you before, and those guys can do it live. So this is offline. That's a bit of a pity, because 2 weeks ago we were in Houston and we were doing about 4,200 tests. And we thought if we use this tool to go through 4,200 tests, that's impossible, right? And so we came up with something that bridges more or less the broadcast engineer and the pure IT engineer. By the way, the pure IT engineer uses something like Wireshark. I guess you all are aware about Wireshark. That's the best tool to get to, but I can guarantee you if 3 gigabit per second fly by and you need to look at it with Wireshark, you don't want to. It's not your best friend at that point. So our architecture of our offline tool is quite normal. Of course, there's a GUI. You need to upload the PCAP file, and then there's some middleware, and there's a DB. By the way, there's a database for just the normal things. You want to know if it's a video file, an audio file, or a combination. And we do have another database for time-related things that we need to capture. Of course, we have some stream preprocessor unit, a stream analyzer, and some storage to capture the PCAP file. But then when we had the idea of going to the event and see that there were 70 plus products that we needed to check, we thought it's impossible just to capture the PCAP file first and then run it through a tool, so we needed to do something. So the workflow needed to be accelerated, and we tried to figure out how to do this with off-the-shelf Ethernet card and be precise as any other tool that's out there on the market. So, what's critical for a success if you want to build something like this? The timestamp on the Ethernet packet should be accurate. So when the packet arrives your equipment, it should be timestamped perfect. And of course, all this stuff needs to be synchronized to PTP, otherwise some of the measurement doesn't make any sense at all. So how does it look like, and when do we have a good capture? If you do the capture as close to the sender as possible. So there are a few options. You can use a tap, just an optical tap, and do the measurement. You can do a port mirror. Be aware, for some switch manufacturers, you lose some of the information like PTP, because they do a copy and they don't copy the CPU plane. Ievgen can explain more. I'm just the dumbass explaining this. And then, by the way, so this is what we say, capture here as close as possible. And you can join the stream somewhere on your network switch. And actually we found out if you join the stream locally on the network switch, it's quite precise as well, so you don't lose too much precision doing that. It depends also on the load of your network. Okay, so where do we go next? If it clicks, yes. So I think we're the beginning of January. We just had our feasts, the 1st of January, and then I said, Ievgen, I need to lock you up in the lab, and you need to come up with a way that we do this precise measurement.
And that's exactly what he did. He was feeding me though,
Yeah.
so I wasn't left completely alone. So
It's quite funny though. You just use a funnel and cheese fondue, and he's happy.
So, what we did, when we were building the original proof of concept, we built a small laboratory setup that. Does that thing click?
Yeah, at the end.
Okay. So we had one single Ethernet switch from a famous vendor. We had a few in-caps and decaps from a famous vendor. We had a commodity off-the-shelf server from a famous vendor. We had a couple of SDI generators, and currently the displayed one is the one we ended up using, which is a Tektronix waveform monitor, which was acting as a SDI generator. It's an overkill, but I'm going to explain why we did that. We also, as a sanity check, we also used another two commercially available solutions on the market. One from Tektronix. You heard about it a half an hour ago. Which is a prism, and another one is a packet storm, which was synced to PTP. So the goal was to come up with a solution to capture all that in a similar fashion and speed up the process of our workflow through the EBU list. So this is this diagram came up after we did some thinking process, and we were picking up what tools we can be using, and we ended up using as simple as possible. We ended up using a TCP dump. So the server itself was equipped with the network card from another famous network equipment provider, which is Mellanox. It was a dual port 100 gig card. There was a reason to go with the dual port because we wanted to be able to use both the port mirroring and the network stream as a multicast stream from the network. The thing is about the port mirroring, when you mirror when you mirror the port on the switch into the card, that port on the switch is not a switched port anymore. It doesn't forward traffic. It just flushes out whatever comes from the source of the port. Therefore, if it's a one port NIC, there is no way to sync it to PTP anymore. So we had to use the second port exclusively for PTP. And of course, it's a dual 100 gig port, but if you use a QSA, you can downgrade it up to RJ45, so you don't have to waste your QSFP ports on PTP only. All the reasoning behind is that there are multiple ways that TCP dump timestamps stuff whenever it captures it. So the default behavior is explained on this diagram, is that the timestamping happens in software on the OS kernel level. This is not what you want to do. That is not precise. So that will not give you the proper measurement results. And actually, if you do the capturing of a source that you know it's going to behave on the network, you get pretty much something like this, which is an abomination. So we changed a little bit our thinking, and we came up with this pipeline. So it's a bit non-standard. That's not something you would normally do, but if you this is a very high-level representation of a NIC and the layers of a data processing in a Unix kernel. But in a nutshell, every single port on the NIC has its own hardware FPGA that does PTP, and it's called a hardware clock. If we use a standard Linux tools like PTPD or PTP4L, you can sync that hardware clock to PTP. Now here's the problem. The port that actually syncs in the data, the packets, also has to be synced to PTP. And if we do port mirroring, that's not going to happen. So there is another tool that is initially designed to provide a functionality of synchronization to PTP and then serving NTP, for example, if a Unix server is a domain controller. It's going to be synced to GPS, to PTP, and then it's going to serve NTP to the rest of the network. That tool is called PHT2sys, and initially it would clock the system clock in the kernel. But there is a workaround, and you can actually tell it to sync another hardware clock internally in the NIC. And if you do it often enough, the precision that you get is similar to what you would have if you sync the actual hardware clock to PTP externally. This is what we ended up doing. So when we went through this pipeline, this is the actual results that we got for the sender that we knew that it's behaving on the network level. This diagram actually shows the correction over time of two libraries. So the blue is the correction per tick of the PTP4L library, and the orange one is PHT2sys. So you can see when you start the daemons, it actually takes some time to stabilize, but then it's a fine line. So the correction between two hardware clocks is neglectably small. It's fractions of, it's a nanoseconds. So when we did the first capture using this new pipeline, there was still something wrong.
And I said many times, Ievgen, something is wrong. We need to figure out what we did wrong.
Yeah,
There's
something
something
is wrong.
with the PTP clock or the synchronization. And he spent 2 days all over the config once again. But yeah, maybe we're a little bit more IT guys than broadcast guys.
I've spent 2 days figuring out that the device that we were using as the IP encapsulator didn't do the frame sync, and my SDI source was not locked to the common reference. So the whole thing was just drifting. And if it is a portion of the graph, but if you take it over a span of multiple seconds, it's literally like Swiss Alps. So that was actually the reason why we switched to using the reliable SDI source that was able to lock to the same SPG. And at the end, there is I talked about that already. Yeah. And at the end, that was the way to achieve a reasonable resources, reasonable. I forgot the word in English.
Well,
Results.
Results. Say it in Russian. So
Exactly.
possible.
So by the time of that experiment, we were using this guy as our main tool, and that thing is about $15,000 US. We did it another iteration of thinking, and we came up with another solution, which is this. And we ended up using this as a main tool for the JTNM tested program. We scaled down hardware-wise, and actually, if you think about Thunderbolt enclosures, Thunderbolt itself provides you with roughly it's supposed to be providing you with 40 gigs per second of bandwidth. Of course, there are overheads. So at the end, we were able to monitor and to capture at the same time about 12 1080p 50 streams of roughly 3 gigabits per second. And before we talk about the results and the actual eye candies and the graphs that you're all here to see, I'm going to hand over back to Willem to talk about the math and the reasoning behind, because he's much smarter than me and does it much better.
So I get the fun part. That's the nice part of today. So actually what it's all about, if you know, well, everybody knows 2110 by now, and that's a suite of documents, and to me there's just one crown piece jewel in the whole suite of documents, that's -21. It doesn't describe video, audio, no, it describes traffic shaping. And by the way, if we go from SDI to IP, the only thing we did change is the network. And when we go from a TDM network to a statistical network, you need to take care of a few things. And this is why -21 is such an important document. At least that's what I think. So, and I guess all the test and measurement guys think the same, so that's lovely. So what does this beast describe? This beast describes 3 different things. First of all, it describes a virtual test for the network in order not to oversubscribe the network, because we're using UDP and multicast. So if we're a little bit too bursty, then we might drop packets in the network. That's actually what you don't want to do. It describes also a virtual test at the receiver side, measured at the sender. So think twice. So what does this describe? It does describe the fact that there are narrow receivers, which, by the way, don't receive wide senders. so that you need to think about it when you buy such things. And there's the wide receiver, which I call it's a universal receiver. You can send it a wide or a narrow signal, and it will receive it. The third thing it's described is a packet read shuttle. There are a few read shuttles. There's a narrow linear, and there's the gapped, by the way. So this bucket. A bucket, it's more or less like a funnel, and it's quite simple. It's like if you want to pour water in a bottle, you use a funnel and you pour the water in. If you pour too fast, the water goes over the funnel and you lose the water, you drop the water. So that's the same with the packets. If the instantaneous level of this buffer is exceeding Cmax, the level somewhere defined in the standard, then you might drop packets in the network. And that's what we said. Don't drop any packet, so don't overflow that buffer. Take a good look at the picture, because I'm going to switch to the next buffer. Does anyone see a difference between those two buffers? It's completely the same. Exactly the same. There's one big difference. Those VRX buffers are read out by the PTP clock. So there's a synchronization thing. This is why we wanted to be sure that our solution is synchronized to PTP and very precise. Otherwise, we can't do a good VRX measurement. So, and by the way, the same applies here. If the instantaneous level of the VRX buffer flows over the VRX max, then you might drop packets. This time on the receiver level. Imagine an FPGA receiver, which is not very flexible in having more memory. Well, that's the type of cases. So the packet read shuttle, on top you see a linear shuttle, and here you see the gapped shuttle at the bottom. In normal words, this is the same as you have a video frame, and a linear packet-based model that's the same as all the packets you need to describe your frame are equally spaced throughout the whole frame. The gap model is, well, there's video has its blanking. During the blanking, we don't send any packets. So if you're a little bit in love with mathematics, then you can think about, oh, the gap here is 4% of the whole video signal, so the bandwidth is 4% more in this model than in this model. Neglectable, but nice to know. So let's take the example of a gapped model, and then let's see how the packets do arrive. And why I show this is the interesting fact here. Well, I can go in all those details, but it's not of use at this moment. But the time gap between two packets for 1080p50, it's about 4.4 microseconds. And for us, it was quite important to know this and to make the calculation and to see how precise the measurement is. And I think we're more than 500 times better than this value. So for HD, we do have a precise measurement. So this was important to know. So some test results. And of course, I could show you the test results of the test in the lab, but those were too good. So let's show you a horrible result. So this is a piece of the interface of our EBO list tool, and it's too small, so I make a little bit of a magnification of it. And the tool says, well, this is I59, RTP timestamp is good, the C buffer model is good, but there's an issue with the RTP sequence, and the VRX model, there's an issue as well. So then we go to the next pane into the tool, and of course, sorry, it's too small, so I'll make it bigger so you can read it from the back. And it says, okay, in order it says it's compliant. It's not compliant, and we detected a linear shuttle, and we detect as well that the C buffer model has maximum one packet in the funnel, so that's quite good for a C. But if you think about it, if it's quite well paced, then your VRX should be quite good as well. There's one problem. I mentioned VRX needs to be frequency and phase locked. And this is actually what you see here. The VRX buffer is underrun for 1,900 packets, more or less. So that's actually what's going wrong. And if you look at this, the graphical representation of our measurement, you see that it's more or less a flat line. So the difference between min and max is about 8 packets or something. No, sorry, it's even less. In this case, it's 4 packets. But it's completely shifted too late. It's about 16 microseconds too late in the normal buffer. You could solve this. The vendor could have stated in the SDP file that there is a TR default, which is different. Or he just can shift the packets, and then he would have a good implementation. So that's a nice graph as well. So I'm the theory guy, so I leave this graph. I leave this graph to Ievgen.
Yeah, I mean, this graph is obviously pretty self-explanatory, isn't it? I mentioned earlier that we did simultaneous capturing with two other tools that are available there. So this graph actually shows the difference in the timestamp of the same packet with the same sequence number of the same stream. And it's also in the nanosecond range.
Yeah.
And as Willem said, the interpacket arrival time is in microseconds range, so we're pretty good. It would not affect critically the measurement.
So actually, we would have loved to have a device that has a PPM input, but we have a 100 gig card and we didn't find any. So mathematically, it's not the best thing to do just to use two pieces of equipment and say record, and then we're going to analyze. So this means that the result is far better than this. And if you look at the outskirts and the maximums, it's still a way less than the 4.4 microseconds. So this is why we're pretty confident that our off-the-shelf solution, which is, if you buy those components, it's about $4,000, by the way, that we could achieve what we wanted to achieve. So, conclusion.
You should, whenever you want to build something like this, you should avoid bottlenecks in the pipeline. So the first bottleneck obviously is going to be the NIC. You probably shouldn't try syncing in 12 gigs into a 10 gig NIC. It's a no-brainer, yeah? So just proving the point, it's not going to work. If a stream is a UHD stream and you don't have a UHD 25 gig capable card, well, too bad. Kernel bypassing, that's another important thing. We ended up using kernel bypass to optimize the performance of the OS. So there was no modification to the actual kernel, but certain NICs provide certain functionalities to offload the packet pacing and the packet timestamping and packet processing from the OS kernel to the NIC FPGAs itself. Use that, because starting from about 3 gigabits per second flying in real time through the OS kernel, you will stop dropping packets not on the NIC level, but on the kernel level. And of course, the storage performance has to accommodate for the speeds that you're wishing to sync in, because at the end of the day, if you're going to use the SATA drive with 400 RPMs, no. So NVMe SSDs are your best friends for that. Unfortunately, you have to invest into those, and that's another bottleneck too. So you will end up losing packets on the storage writing speed level. Yeah.
Okay, and as mentioned, and we cannot repeat it enough, frequency and phase lock. So use the NIC that has the hardware clocking and the timestamp support, as mentioned before. And oh yeah, by the way, if you do a setup like this, don't forget that your server might be automatically trying to sync to NTP. Switch that off, otherwise there's some sort of a conflict going on. It took us a while as well.
Yeah, you should really pay attention which clock you synchronize into which clock, because it caused us a lot of pain while we were trying to synchronize the clock, and we realized the NTP was pushing its data, and then we saw jumps on the graph. It was really not fun to troubleshoot.
So by the way, last year's you also, probably the JTNM roadmap, it's somewhere at the back, a small version of the JTNM roadmap. On the right top hand side you see the green bit, the green pastures. It's going to a software-based solutions. And I think we more or less proved that just with off-the-shelf equipment, we can be very accurate and we can do those measurements without any hassle. So, by the way, that was the latest setup that we showed at the production technology seminar at EBU. On the left-hand side, you see this test setup with the Prism, the Tektronix generator, the PTP clock, and on the right-hand side, this is what we ended up with. So we carry this in our carry-on luggage to the test event.
Yeah.
So easy it is.
Still will not give you real time though. So.
By the way, if you want to know more about this open source project, you can just go to the website techebuch/list. If you're a programmer and you're fairly happy with compiling C++, go to GitHub. If you say, a bridge too far, use our Docker. If you say, well, Docker is even a bridge too far, just go to listebu.io. We do have a dematerialized version of this beast. You just drag your pcap file in and all the calculations will be done. And as Ievgen already mentioned, we use this beast to capture and test everything during the test event together with Tektronix and a few other very good equipment. So voila, I think that's about it. So thank you.
Thank you, gentlemen. Do you have a question?
So I saw that you were using mainly Mellanox. Do you have any experience with working with any other NICs and their, different kernel bypass like DPDK and any performance that you had with that?
That is the question we get a lot. If, in principle, the TCP dump is agnostic to whatever kernel bypass you're using, if the API allows it, if the NIC is capable of doing what we're doing, if you're just going to be using an Intel card that has only one port, if that card can be synced to PTP, even without a kernel bypass, you can still try to sync in at least one HD stream. With your experience may vary. Sometimes you have to repeat it multiple times. There is a TCP dump report, how many packs were dropped on which level, and you will see if it's good or not. And we did not experiment with other offload APIs.
Thank you, gentlemen, and have a good afternoon.
Thank you.